For an extremely extensive stretch, people have conjectured about what presence may resemble on different universes. On account of the James Webb Space Telescope, the most exceptional telescope in existence, this question can at last be addressed. While examining the closest star system to us, Proxima Centauri, which is simply 4 light-years away, researchers have noticed a few uncommon peculiarities from one of the planets in the system, Proxima B. These irregularities, alluded to as artificial lights, have confused the most brilliant minds in mainstream science. Yet what are they? Do these lights infer the presence of intelligent life on the planet? Join us as we dig into the James Webb's surprising revelation of city lights that change everything. The only life that we currently perceive is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To embrace such an interstellar pursuit, American cosmologists Jill Tarter and Thomas Pearson started the search for extraterrestrial intelligence, SETI, project in 1984. The charity's objective is to gather spaceborne radio transmissions. Radio waves can travel further and are consequently more likely to be detected by the 42 radio telescopes that comprise the unique Allen Telescope Array in the Californian Sierra Mountains, as they are less scattered or absorbed than other kinds of radiation. However, in the past 30 years, no obvious extraterrestrial transmission has been found. Hence, the James Webb Space Telescope's successful launch aided the quest to explore a range of distances and unseen planets circling distant stars. The largest telescope on the planet, which is drifting roughly 1 million miles from Earth and outfitted with incredibly delicate detectors, will be used. A while back, there were no known planets beyond those in our solar system. Yet since then, over 4,000 exoplanets have been found circling different stars. According to NASA, the universe could contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial vegetation. The Galileo spacecraft turned its instruments back toward Earth while en route to Jupiter and found an obvious indicator of the presence of plants. The instrument detected the vegetation red edge, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth, shrouded in a jungle, should have a strong and easily discernible red edge. The JWST will measure the red edge of distant Earth-like planets in the habitable zone around stars. These could be significant markers of life in the exoplanet atmosphere. When sunlight passes through a planet's atmosphere, the JWST could detect it as it enters its atmosphere. The light's missing frequencies would then be identified through spectroscopy. Ions and atoms in the atmosphere absorb specific frequencies, creating a distinct fingerprint that the JWST can perceive. This process might be used to learn the composition of the atmosphere and if life is plausible. Most likely, life could exist on Earth-sized planets with atmospheres similar to ours, with a prevalence of oxygen, nitrogen, and carbon dioxide. By looking for components that are not regularly present, one might detect technological life. Chlorofluorocarbons, CFCs, produced for refrigeration and cleaning products, would likely be detectable to extraterrestrials observing Earth's atmosphere from afar. If the JWST identified CFCs in planetary atmospheres, that would be a clear indicator of civilization. In fact, life on exoplanets might not resemble life on Earth. Sometimes even natural life, like extremophile species, can seem alien. This is a group of organisms, primarily microbes, that can survive in conditions where other living things would die. Some can endure temperatures up to 250 degrees Fahrenheit, some can survive cold as low as -4 degrees Fahrenheit, and some can survive in highly acidic environments with pH levels below 3. Others can be found on Earth where we wouldn't expect to find any life at all. However, since planets like Earth are more likely to support life than planets with extreme temperatures or acidic conditions, it may be wise to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are rarer and usually have shorter lifespans in our universe. The likelihood of studying planets orbiting red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. There is more opportunity for the development of life and evolution to create complex life forms because these stars have longer lifespans. Located approximately 40 light-years from Earth, the TRAPPIST-1 planetary system will be the focus of JWST's first mission. It orbits a cool red dwarf star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone could have liquid water on their surfaces. The TRAPPIST-1 star, despite having a much smaller and cooler mass than our Sun, emits light similar to that of Earth. Due to the close orbit of its planets, the most plausible opportunity for us to see city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Our closest star, Proxima, is multiple times fainter than the Sun, so a planet would need to be much closer to it than Earth is to the Sun for it to support life based on liquid water. In August 2016, astronomers found a planet with 1.3 times the mass in the habitable zone, or Goldilocks zone, where the light intensity is just right to allow water to remain liquid. Proxima B orbits Proxima Centauri. If it is possible, Proxima B might be an airless dead planet, given that it orbits its red dwarf star, Proxima Centauri, at a distance of only 4.6 million miles. The planet Proxima B is in a close orbit that exposes it to strong solar winds that could strip away its atmosphere. It also receives enough sunlight for temperatures and liquid water that are nearly identical to those on Earth. Due to its proximity to the star, Proxima B is believed to be tidally locked, always showing the same side to the star. Similar to Earth, Proxima Centauri is about 18% the mass of the Sun and shines much less brightly than one might expect for a planet so close to its star, only 5% of the Sun's brightness. This may be expected to be a superhot ash, though liquid water could exist on Proxima B as long as the planet has an atmosphere to retain heat, since the total energy reaching it from the star is only 65% of what Earth receives. Currently, the planet is not particularly inviting to life. It is probably tidally locked, meaning it always faces the same direction towards the star, causing significant temperature variations. The planet also receives 100 times more high-energy radiation than Earth does due to its proximity to Proxima Centauri, including X-rays and ultraviolet light. Proxima B is also bombarded with high-energy particles during star flare-ups. Unless it has a protective magnetic field like Earth, however, there are some plausible conditions that could make it a habitable world. Models suggest that the atmosphere of tidally locked planets might be prone to rapid breakdown due to the freezing out of volatile gases on the night side. A planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we can't even estimate whether the planet has an atmosphere. However, since an atmosphere implies the presence of CFCs, and the two combined suggest the presence of life, we are eager to find out if Proxima B has an advanced civilization. It could have solar panels covering the day side to generate power to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has sparked a race to determine whether it transits its star as seen from Earth. These transits would allow researchers to determine the planet's size and mass, which would then enable them to learn its density. Knowing this would confirm the planet's rocky composition and provide information on the materials used to form those rocks. During a transit, starlight could reveal the nature of the planet by passing through its atmosphere. However, the probability that the orbit will be aligned for researchers to observe a transit is only 1.5%. The star's tendency to flare also complicates matters. Astronomer David Kipping of Columbia University says the star is unstable. As a star's heat makes a rocky planet absorb sunlight and re-emit it as infrared light, rocky planets produce a unique type of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was specifically designed to study infrared light. Proxima B's infrared heat signature is crucial for identifying the planet's atmosphere. Furthermore, the infrared part of the spectrum has strong signals for water. The JWST will be able to detect artificial illumination on Proxima B's night side, even if it were as faint as what our civilization currently uses on the night side of Earth. JWST could detect artificial lighting as long as it was confined to a frequency band that is multiple times narrower than starlight. Proxima B's day side is heavily covered with solar panels due to its unique spectral edge capacity to reflect starlight. As Proxima B orbits its star day in and day out, Its day and night temperatures would be crucial for determining how much heat is still retained. JWST will monitor Proxima B's night side despite the planet being extremely cold. JWST's infrared vision will help find artificial light when light from the night side passes through the atmosphere. Researchers will use JWST to analyze it. Exploring the potential for extraterrestrial life has captivated scientists and enthusiasts alike for decades. The advancement of space telescopes, such as the James Webb Space Telescope, JWST, has provided unprecedented tools for examining distant worlds and their potential habitability. Beyond Proxima B, there are numerous other intriguing targets in the search for signs of life. One notable example is the TRAPPIST-1 system, which includes several exoplanets within its habitable zone, making it an ideal candidate for further study. The TRAPPIST-1 system is a particularly interesting target due to its arrangement of 7 Earth-sized planets orbiting a red dwarf star. These planets are of significant interest because their proximity to their host star places them in the habitable zone, where conditions might allow for the presence of liquid water. Given that liquid water is a fundamental requirement for life as we know it, studying these planets could provide insights into the potential for extraterrestrial life. The JWST, with its advanced infrared capabilities, is well suited to study the atmospheres of these exoplanets. By analyzing the infrared spectrum of light passing through a planet's atmosphere, scientists can detect the presence of key molecules, such as water vapor, methane, and carbon dioxide. These molecules are often associated with biological processes, and their presence could be an indicator of life. Additionally, the JWST's ability to capture detailed images and spectra allows for the analysis of atmospheric composition and weather patterns, which can offer clues about the planet's climate and its potential to support life. Another fascinating target is the exoplanet Kepler 452b, often referred to as Earth's cousin. This exoplanet orbits within the habitable zone of a star similar to our Sun. With a size and orbit comparable to Earth's, Kepler 452b presents an exciting opportunity for scientists to study a planet that could potentially have conditions similar to those on Earth. The JWST's observations of this planet could provide valuable data on its atmosphere and surface conditions, enhancing our understanding of how common Earth-like planets might be in the galaxy. In addition to studying individual exoplanets, the JWST will also contribute to our understanding of planetary systems as a whole. By examining the frequency and distribution of exoplanets in different types of star systems, scientists can gain insights into the formation and evolution of planetary systems. This information is crucial for determining the likelihood of finding habitable planets and understanding the broader context of our place in the universe. The search for extraterrestrial life also extends to the study of moons within our own solar system. For example, Europa, one of Jupiter's moons, is believed to have a subsurface ocean beneath its icy crust. The potential for life in such an ocean is a subject of intense scientific interest. Missions like the Europa Clipper, which is scheduled to launch in the coming years, aim to explore this moon in detail. The JWST could play a complementary role by studying the outer regions of our solar system and detecting any potential signs of activity or atmospheric interactions. Furthermore, the study of comets and asteroids provides additional opportunities to understand the building blocks of life. These objects are considered remnants from the early solar system and may contain organic molecules or other compounds that could shed light on the origins of life. Observations of comets and asteroids using the JWST could reveal the presence of complex organic compounds and provide insights into the conditions that might have led to the formation of life. The quest for understanding life beyond Earth also involves examining the potential for life in extreme environments, both on other planets and within our own solar system. For instance, the study of extremophiles, organisms that thrive in extreme conditions on Earth, provides clues about the types of environments where life might exist elsewhere. By understanding how these organisms survive in extreme environments, scientists can develop models for what kinds of conditions might support life on other planets. Additionally, advancements in artificial intelligence and machine learning are increasingly being utilized to analyze astronomical data. These technologies can process vast amounts of information quickly and identify patterns that might be indicative of extraterrestrial signals or other phenomena. The integration of AI with the data collected by the JWST and other observatories could enhance our ability to detect and interpret potential signs of life. In summary, the exploration of exoplanets and the search for extraterrestrial life is a multifaceted endeavor that involves studying a wide range of celestial objects and environments. The James Webb Space Telescope, with its advanced capabilities, is poised to make significant contributions to this field. By examining exoplanets within habitable zones, studying planetary systems, exploring moons within our solar system, and analyzing comets and asteroids, scientists aim to expand our understanding of the potential for life beyond Earth. As technology continues to advance and new missions are launched, our knowledge of the universe and our place within it will undoubtedly deepen, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe?